Okay, so section 2.2, definition of the derivative. The definition would be instantaneous rate of change of a function at a point p, abscissa a and ordinate f of a. You could also use x and y. The slope of the tangent is the graphical representation of the derivative, and this is the mathematical representation of a derivative. This is the change in ordinates. This is the change in abscissas. This is actually, to be accurate, the result of the simplification of the subtraction. It originally was this. As you can see, it's a position, and this is a position, like this. This is x, this is x plus h, this is, whoops, this is x plus h, and this is h, of course. So when you subtract them to get the change, you get h, because you do x plus h minus x, so you get h. And so change of ordinates over change of abscissa, same thing as in, for example, you could say distance over something, or like, you know, like displacement in the y, displacement in the x. So that's how we get the slope, which we would call in here derivative. So this is the formal definition. Why does h approach 0? Because you need the slope to be as accurate as possible, so you're trying to achieve the smallest interval that would apparently in the end up touching it like a tangent rather than a secant, with, you know, inaccurate slopes. Instead, you try to approximate it to get as small as possible to end up somehow getting a tangent like this. Like for example, when we approximate it by graphical, like when you get your ruler and I ask you to get the slope of this point, for example, and you get your ruler, what you actually are doing, you're taking a patch like this, you're taking a patch and you're trying to get the slope of this patch by putting your ruler on top of it and seeing where the point fits, which is inaccurate, but it's good enough to give you sometimes the slopes. So yeah, this is again another notation. This is at a point, so you can do this, and this is an exercise. Let's do this quickly. So this is the formula, right? So we need to substitute this into the original x. This, well, it's the same thing, so you just rewrite it and you put h here. So let's do that. So you get x plus h plus 1 over x plus h minus x. Let me just rewrite that quickly. Okay, so x plus h plus 1 over x plus h minus x, and then this is in the same bracket, in the same parenthesis, so the minus the minus distributes, so you get minus 1 over x over h. So x and x cancels, you're left with this. I would want to multiply by a common denominator, or a denominator that makes these two common. That would make this x and this x plus h, but for that to work I must do the same so that it cancels out by 1, so that I didn't change the given. So you're left with h plus x minus x plus h over x plus h into x. X and x cancels, you're left with minus h. This is minus h over here because the minus distributes, as you can see here. And I don't like the minus here, so I'm going to put it here instead. So the minus would be here over h. So what you're left with, let me rewrite it, it's h minus h over x plus h into x over h. Well, for me, I can factor, like you can, I can do this, and this will be 1, and that's how you factor. Try putting h again, you get the same answer. With that, you cancel and you're left with 1 minus 1 over x plus h. There's one mathematical thing that I did incorrectly, which is not writing the limit here and there and there and all. You need to write it, and you need to keep the limit as long as you are not in the step where you substitute, which is somewhere here. Yeah, I know here, yeah. As long as you didn't substitute, as long as h is still there, you need the limit. But for me, I'm writing like just on the spot, so just to show you as a demonstration. So yeah, so put 0 instead of h, you get 1 minus 1 over x plus 0, so that's x into x, that makes x squared. Now what they're asking for, of 2, so put 2. 1 minus 1 over 4, that gives you 3 over 4. And did I get the same answer? Yes, I did. What values are undefined? That's what they said for g and g prime. 0 here and 0 here, as you can see. So next one. Okay, so this one's easy. You just put x, let's do it together. Limit of, as h approaches 0, of what? Of c. This function is called c, so c plus c into, okay, I hate putting c's in parentheses because they look alike. X plus h minus c into, again I hate this, x over h. Okay, so the limit of h as it approaches 0 of what? Well, x plus h, put there, you get x plus h cubed. And you're left here with, you know, the casual x cubed over h. Expand, you get here, well, remember this, like, I wouldn't say memorize, but like get familiar with it. For example, for the squared one, you get x squared plus 2xh, and then plus h squared. For this one, it's going to be the same power at the beginning, and then you have a coefficient. There are multiple ways to do it, but I'm not going to go through the process. And you multiply by x squared because the power decreases, and then you have h. Again, the exponent repeats, h plus h squared because again the power increases for the h, and then this one is cubed minus x cubed. These cancel, and here's h. Limit of h as approaches 0. You factor the h out because it's very tempting, especially when you have an h down here. Factor the h, you get 3x squared plus 3x h plus h squared over h. Cancel, substitute immediately. 0, 0, you're left with this. We're done pretty much. So with that, this is another function. We're not going to go through them one by one, but here the trick is that they multiply by the conjugate, because if you do it this normal way, like let's say stop here, put 0, 0, 0, like you still have an h here, so you need to cancel somehow. So here it's very tempting to see that there's an x and minus a, x and minus a. So if you were somehow merging these two, subtracting them, like somehow merging these like this, and then subtracting them like this, x plus h minus a minus x plus a, it's very tempting to do this and then somehow get rid of this stupid radical, and you end up with an h and you just cross. So how do you do it? Well, you multiply with the conjugate. What does that give you? It allows you to square this and square this, and that makes you able to subtract these immediately because they're out of the radical. You don't have to worry about anything. So it's x plus h minus a minus x plus a immediately, like without the radicals, like this, which is what I just showed you, but instead without the radicals, minus x plus a. So that's how we're left with h up. And then even though you have this scary denominator down there, it doesn't do you harm because it's not as scary as the denominator down here, because you here at least have a plus that would guarantee, and here you have x and a, so it's safer. And you actually do end up not seeing that if you put 0. It's just that this goes away, and then you just end up with having a 2 because same values add up, they give 2 times. So that with that we're done. This one's really easy. Just do it again, x squared plus 2xh plus h squared over h minus x squared, like you do it like that, and then you factor h out. For me, I'm just going to cancel immediately, and then put 0, you get 2x, and that's pretty much it. Here, I'm not going to do them one by one, but you'll do it the same way, to be honest. You'll do it the same way. So with that, we'll just continue. This is just the definition of a normal line. Normal line, well, all I need to say is that the slopes are like the slopes are reciprocals, the negative reciprocals of each other. So, and this is the graphical representation, basically. Like this one's positive, and this one's negative. But if you were to just do normal positive negative, you'd end up with this. This is if you do positive negative. That's why you need the reciprocal. like if you have a change in x and a change in y, it graphically must be like this. Do you see how things are going? Do you see how there's this one special relation that you can see? You can see that some angles are equal and somehow just like there's some kind of rotation happening. As you can see, this is this you could call it the beautiful property of I don't know, like it's some kind of mirroring or rotation. But anyways, so let's move on. So they're just continuing on the fact that you have like you already know the relation between the slope of the normal and the slope of a tangent, the normal being -1 over the tangent, and the same applies to the tangent, -1 over the normal. And you get the derivative and you already have the equation of the curve itself. You're given the x, from the x you can get the y, and the two will make the point. The two values, or the x and the y, make up the point like this. And you can get the slope by putting the x. With these two you'll get the line, and we said to get the slope of the normal you do -1 over the slope of the tangent. Again, you can get the line, same y0, same x0. So there you get the equations and you're done. So for this one I have a special explanation, to be honest. So one way I would explain this is, well, there's this one simple way that you can develop on your own. Like I can explain it in a brief way and you can use it, you can develop it and explain it to others, for example. Like, because I personally haven't developed this one, I've developed another one, but don't worry, I'll explain both of them. So say that you have A and B right here. So this is on your left, for example. This is on your left and this is on your right. B is to be honest, B is the closest to your right hand and A is the closest to your left hand, right? This could simulate where your right hand is, and this could simulate where your left hand is. So I will ask you to use your right hand and try to approach A. This will happen in 3D. Your right hand somewhere here in this region will go from here to there in this manner. But I don't care about the 3D, I care about your 2D, which will move in this net movement, in this plane of the screen. So it will move like this, from right to left, right? It will move from right to left. And if I ask you to use your left hand to approach or clasp B using your left hand, your net movement will be like this, from left to right. So let's take a smaller scale, AB. So I asked you to use your right hand on A, so I'll call that the right hand derivative of A. By the way, even though I asked you to do just clasp, I never asked you to do derive or anything, but let's just skip that part and just say it's derivative. What I care about is the direction, not the process. So right hand derivative, when you're going from right to left. Left hand derivative is when you go from left to right. So with that, right hand derivative, we said from the right to left. Left hand derivative from left to right. So with that, how can you imagine it? You can use this way. Clasp your hand, do the opposites, make sure it's opposites, because if it's not opposites you'll get confused. So yeah, if this way confuses you, it's fine. I have another way. You can use the two, actually, to be honest, you can merge them, but let's just use this way, for example. So we use the notation minus and plus on top of as a superscript, right? So to explain what that is, basically it's like this. This is A plus. To be honest, this is A plus, and this is B minus, and this is B plus, and this is what? This is A minus. So what is A plus here? A plus is nothing but a number or a value or a position right in front of A. By right, I'm not saying right left, I'm saying exactly in front of. So A plus is right in front of A. A minus is right below or to the left of or behind A. B minus is right behind B. B plus is right in front of B. So in this case, this is a pretty decent explanation, because using this you can actually avoid certain mistakes which I'm going to discuss right now. These are some intricate details, but this is necessary for like a general understanding, I guess. Like you can discard this, you can skip the video, you can do whatever you want. But for those of you who are interested, for those of you who believe that this explanation could help you, this can strengthen your general knowledge about math and possibly make things easier for you in general, then I'll do my best in this part. So because building intuitions is one thing that I really love doing. So x, y, and they generally help me, and they can help the rest to, like, you know, like visualize stuff. It can make you do stuff quicker, like, basically pretty much. Anyways, so if you were to have a function like this, okay, let me just edit. Okay, so you have it like this. Okay, and now I ask you, give me the left hand derivative of, let's say this point is, this x here is 1, so this is at 1 and this is also at 1. So give me, no, first of all, tell me, is this function right hand differentiable at 1? Is it right hand differentiable at 1? So let me help you. Right hand differentiable, right hand differentiable is going from right to left, right? Right hand differentiable is 1 plus in this case, because you were taking 1, so 1 plus. 1 plus means right in front of it, but as you approach towards it. But this value does not exist. This value does not exist. It's not defined. So in this case, because it's not defined, it's not right differentiable. From here, is it left differentiable? This is the tricky part that I want to explain. Is this left differentiable? Well, some of you will say yes, some of you will say no. Who is right? Is it left differentiable or is it not? Well, if you now use what you learned here, what does it mean left differentiable? It means, for 1, it's 1 minus. 1 minus, where is it? It's right here. For 1 minus, what do I care about? I haven't told you this, but I'll tell you now. What I care about is this box region. For an A plus, this is the box region I care about. For an A minus, this is the box region I care about. The small tiny area from the A minus to the A is what I care about. From the A plus to the A is what I care about. For the B plus to the B is what I care about. From the B minus to a B is what I care about. So this small distance from A plus to A, this exceptionally small distance which is right here, is what I care about. So I don't care if here it's not undefined, here it's undefined, the function is going helly and crazy and I don't know what here, whatever I said. Anyways, so I don't care about any point right here. I only care about a small tiny segment which is right here. I could be wrong, but I strongly believe that I'm not. So basically you only care about the small tiny patch which includes the point, because what you're gonna do is you're gonna equate this to the point itself for it to be right differentiable or left differentiable, by basically doing, for example, something similar to this. Also, when you talk about these kind of intervals, let me discuss them now than later. So for this one, you have this is called closed interval, this is called open interval, and this is crazy, but it's a format that people use. This is the same as this. It looks funny, but it's the same. Imagine you are enclosing the outside. You're enclosing the outside. Imagine these are some kind of arms, some kind of square lasers. You're killing everything in front of it, and it's dangerous to be on it. So you're left with inside of it or behind it. Behind, yeah, that's a good word. Behind it. So you're not on it. So that's why this is the same thing here. Here, you are tangent to it, but you're not on it. You're not inside of it. You're just right in front of it. Here, you're including it. Here, you're tangent to it. Here, you're excluding it. Because you're scared of it, you're behind of it. For example, this is just one way to remember it. I think I explained everything. Just one last thing is when you're discussing differentiability in A, B, you only care about from A to B, right? You don't care about anything behind A, anything in front of B. Because of that, you discuss right differentiability at A, left differentiability at B. And let me check. Right differentiable at A, left differentiable at B. We're done. For those of you who listened to this minute or the second, thank you, and we'll be moving on to the next page. Okay, so one thing to discuss, I'm not going to solve most of those, but I'm going to give you tips and tricks and things to be aware of. So first of all, you have a 0 here and you have a 0 here. You have a 0 here and you have a 0 here. To be honest, what 0 is what 0? What are you placing here? If I told you you're approaching 1 plus, will you put 1 here and keep the 0? Will you put 0 here and keep this and put this 1? Will you put 1, 1? Or will you do nothing at all because it remains 0? And what happens if I put 1 here and 1 here, 1? So this can get confusing, but let's not fret. This is nothing but the change in the x, and this is nothing but the change in the y. This being the x, this being another x, and so on. So what is your x? Your x is 0, 0, 0. So where do the zeros up here come from? They came from this. One more thing to explain this. We said 0 plus. Do you see a plus here? Nope. Do you see a plus here? Nope. So the point is, what you're using here is your x. So your x is 0, put 0. Your x is 1, put 1. Your x is 3, 3, minus 3, minus 3, so on and so forth. So do not get confused. It's x plus h of, like the function, like, get the ordinate of that, minus the ordinate of x itself. Here x happens to be 0, so yeah. Plus, you don't replace h at the very beginning. So that's another hint. That's another hint on why it's not 0 plus or 0 minus or any number they give you. It's because h generally, especially when you see an h, if you see these h's, it means they haven't been replaced. So there's no way that this is 0 plus or 0 minus or 1 minus or 0 or 1 minus or 1 plus or anything that they can ever put here. So with that, it's this is the x, this is the h, and so on. So I hopefully gave you an idea in the exam, like 3 multiple, 4, 3 or 2 ways, or any number of ways I gave you that I didn't count, to be honest. But I hope that one of these ways will help you determine like which one's x, which one's h, which one's the, if you get 2 zeros, if you get 1, if you get 2, if you forget where to put. I hope this clears this problem out. So you put the h, you get h radical h, 0, again, a very nice number, everything gets cancelled out, h radical h, h cancel, and you're left with radical h. 0 plus is a nice number because we have here a radical, so you get a positive number. This is initially positive because it's right in front of the 0. If you have 0 minus, you'll have to say sorry, but it's undefined. So pretty much. Non-differentiable at points of discontinuity. Why? Because they're just showing that I mean, you can read this on your own, to be honest. Explaining it might help, but it's just that they're comparing the for example, the limits of the right hand to the limit of the left hand, the differentiability of one on the other, just like how they proved in the other section. They proved why it's necessarily continuous, so they're just doing kind of like the same thing here. So let's just skip over this. To be honest, I would love to explain every single bit, but time doesn't allow as much, and sometimes it's not necessary, I guess. When you're worried about other stuff, you have other exams to study for. So I'm not going to go into depth or detail. Now, this is one thing that sometimes can confuse people, is the piece element thing, or whatever it's called. So you have a function of 2 pieces, and if you're looking for differentiable at 0, you'll have to look for right hand differentiable and left hand differentiable. So this is x less than 0, so it's from 0, not counting 0. Let me just draw it like this. So not 0 all the way down to minus infinity, and this is 0, and this is here is 1. I mean it's including. So think of this as a number line, and I did it overlapping. I mean, I didn't put them overlapping so that you're not confused or that it's not messy. So this is x is 0, and this goes all the way to plus infinity, this goes all the way to minus infinity. So you're going from 0 to plus infinity. This is the piece which is right here. This is exactly how you can envision the domain, and this is the domain of the other one. And yeah, pretty much just do the derivatives. You check the zeros come from where, come from here, and just place them, and you can do this yourself. A differentiable function is necessarily continuous. Oh, this is the one I just talked about. Well, anyways, so we're pretty much done with this page. So here we're asked to prove that this is not differentiable. Well, this is easy. Differentiate one side and differentiate the other. So left-hand derivative and right-hand derivative, and you will notice that one is plus infinity, one is plus infinity. Undefined limits. Basically, I mean, even though they're plus infinity, they're pretty much undefined, because you can't say that a line has a slope of plus infinity. Pretty much saying you have a vertical tangent, no less, no more. So with that, it has an undefined slope, it's a vertical tangent. That's one important part, is that there is a vertical tangent, but that's useless to us when we're talking about differentiability, because a vertical line has no slope that you can talk about. It's undefined. And so with that, we'll move on by labeling this as a vertical tangent example. Now, a corner point example would be absolute value of x, famous for its corner point right here. So with that, you can generalize that corner points are points where the slope is suddenly changing between two values. Like, for example, here you have a minus x, that's a slope here, and you have here x. Suddenly at that point, you can't even determine the slope. Okay, wait, let me ask you, wait, let me just, why is there a circle here? Okay, so is it horizontal? Is it like this? Is it like that? Can you even determine the slope at this point? No, you cannot. There's just as you say, for example, a minus here. If you say a minus right here is here, a plus is right here, just before the corner point. They have slopes, and they do exist. At that point, the slopes meet. I mean, or at least, no, the points meet. What about the slopes? You can't really do anything to that. They don't exist, because there used to be two just right before it. It's like, for example, two people talking to you. Can you respond to them or hear them, both of them, at the same time? No, you cannot. Same thing here. The corner point will not take a slope, because both of them are approaching it with the same slope. Take my slope, take my slope. So which one will it take? It can't take either, so undefined. Sorry, corner point, so pretty much it will stay undefined. So here you have an example, and you have two pieces. One nice representation of this is, I do this, by the way, the following. I usually show domains like this. Wait, actually ignore what I did right now. For example, x less than 1. Less than means not including, so I draw it as a circle. Less than 1 means you go all the way down. Is there a limit? Is there a piece that's continuous? No. So I'll just end with an arrow saying minus infinity. And here, what is the point? 0. So let me write 0 here. So, oh sorry, not 0, 1. Yeah. So x is greater than or equal to 1. Greater than or equal to. So the point is included. So let me draw a line showing that it's included. This is just me defining my own symbolism, or my own symbols and my own terms and my own. But these things help. Plus infinity, because there's no upper bound, there's no upper limit. Same thing with here, there's no lower limit or lower bound. So you're left with this diagram. This diagram shows you the pieces. It shows you the domain, pretty much, of the pieces. This piece has this domain. So from this point, including it, all the way till the endless limit of the plus infinity from here. And here it's not including this point, so you can draw it like this. Not including this point, all the way towards the end of the minus infinity here. It looks cool, right? So anyways, so show that g has a corner point at x equals to 1. Pretty much do the left-hand derivative, do the right-hand derivative, and that should lead you with, well, what they got here is these two. Also, one important point. Remember how we do the derivative? We said the formal derivative was the following. It was limit as h approaches 0 plus or 0 minus, because this always, by the way, will be 0 plus or 0 minus. It will never change. Why? Because we're trying to get the difference in abscissas to be nearly 0. So you have a 0 plus and a 0 minus. H can never, I was gonna say two words at the same time, can never approach another number other than 0 plus or 0 minus in this example. Otherwise it will be useless. Otherwise you have to change or mess around with your functions, pretty much. So what you're trying to do is you're trying to get a difference of 0. That's why you need h to approach 0, so that your x plus h approaches x, so that you do x minus x instead, but in a formal way, or in a limited way, in an approved way, mathematically existing way. Or anyways, so with that, so this will never change, 1 minus 1 plus. In every single question should stay the same. If there's an extra trick, which I haven't seen yet, if they would change this, they have to explain it by doing some other change here. But anyways, this will otherwise remain 0 minus and 0 plus. 0 minus for left-hand derivative, 0 plus for right-hand derivative. So with that, this will be the x plus h, and this is x, so this is your 1. Here you look at the function that contains it. This contains it, so it's this upper piece. Or you can look at from here, it contains it, so it's upper piece. So you put 1, you get 2. So that's how you always so not I mean you put 1, you get 1 squared, which is 1. Sorry. So here you always get 1, you always get 1. So you don't even need to confirm the next time you do this, or even when you have a 3 piece, you don't have to confirm this. You immediately go g of 1 is always going to be 1, because this is defined to be 1 here. No matter how many pieces you have, and no matter how many left-hand, right-hand derivatives you're doing in that one part, as long as you're talking about a point that's defined, you're always going to be using that point. So so it's always the same value here. The only changes here, that's what changes. And then from there you get different values. Here you get 3, here you get 2. That makes it a corner point, because the derivative or the limit of this as h approaches 0 does not exist. Why? Because the left-hand derivative is not equal to the right-hand derivative, signaling that there's a sudden shift in slopes. So definitely it has a corner point. It's not differentiable at that point. That's pretty much it. So next page. Here I guess there's nothing new as much. They're talking about the chain rule, but they're proving it right here. If you're interested, you can see it. Personally, I am interested, but I'm not going to read this now. Maybe I'll read it later. But anyways, they reach to the conclusion. Let me simplify this for you. They reach to the conclusion that when you're doing the derivative of a function, they're talking about functions containing functions. So for example, f of x is a function. Now say this function is contained in a function called g of x. What's the derivative of this entire thing? This is basically what they're trying to do. What is the derivative of a function that contains another function? How do you do it? By the way, why do we want to put a function in a function? Because 3x is a function, x squared is a function, sine x is a function. So when you're doing, for example, when you're doing f of sine of x is a function, a trigonometric function. F of x is a function. So a function of a function, that's why you care about when you do it, when you derive, pretty much. That's why it's important. So pretty much what they're trying to say here is that when you derive this, so g of f of x, when you derive this, you pretty much do g prime of f of x, that's the prime of the g itself, times the prime of what's inside, f prime of x. Did I match what's here? Well, I should have. So g prime of u prime of g prime of u of a times u prime of a. Excellent, we did the same thing. What does that mean? That's the same thing when you do, for example, sine 2x. What do you do here? Well, you take out the 2x and you derive it, so you get 2. And what's the derivative of sine x? Cosine. And that's pretty much what you do, right? Chain rule, nothing less, nothing more. This seems to be what they're talking about. It follows that whenever g is differentiable at blah blah blah. They happen to have another diagram for it, probably continuation of the proof, and they're talking about intermediate functions. One thing to talk about that's really nice is how when you have, for example, you have g, you have u, you have f, you have x, you have z. For example, say that you have all those are functions. Yeah, functions. just double check something. Yeah, functions. Okay. So if you're doing the derivative, for example, of g dg over dx, dg over dx, let's mess around. Dg over, well, let's put an intermediate value, du. Here I want to cancel, so let's put du. Over, let me mess around a bit more. Let me put f. Okay, df. Let me mess around more. df. Okay, I mean, sorry, to cancel. But now let me mess around. So dz times dz over. What do I want to reach? dx. We're done. So this is just, I'm showing you how we can do this. Is pretty much what the chain rule is all about. The chain rule, this is how you can actually see why it's a chain. Do you see why it's a chain? So the chain rule is there for you to reach intermediate values. So instead of doing the derivative immediately of a point or of a curve, for example, you might be doing the derivative of this and the derivative of this and like certain tricks here and there. So that's pretty much what they're talking about. So this chain rule, well, I mean, I'm not sure, probably this is mathematically wrong, but it looks like you can do this and just immediately end with this. Well, you're not entirely right, but you're also kind of like not entirely wrong. But so I'll just stop there for that, in that part. Not to be too specific, not too detailed, or so let's move on. So in here it's really easy, you just do the chain rule you learned from the previous page, so, or like from what you remember. So it's 4, you bring it down, and then you have here 4 minus 1, so 3, into the derivative of this, what's inside. So x squared plus 1, so that makes 2x. Multiply these two, so you're left with 8x into x squared plus 1 cubed. That's what we have here. And here, same thing, you just have to do it longer, but notice that you have a function and a function. These are not as simple as I don't have anything here, for example, so you do chain rule. But here you have two multiplying each other, so you have to do product rule. And then from product rule, you notice that this is y1, right? y1 is or needs the chain rule, and then y2 also needs the chain rule. So what you're going to do is, first of all, start with the product rule, as you can see right here, and then you're gonna move on with the chain rule for each one, and then you're just going to replace all of that, simplify, and get this crazy polynomial right here. So anyways, even though they give us this in the example, probably just to show you, here in the activity it's really easy. Like, to be honest, you just need to do this 3 into 4x cubed minus x squared minus 1 squared into derivative of this, that will be 2x squared minus 2x, and you're done pretty much. Here they summarized for you the derivatives. To be honest, you don't need to look at this table. The only important ones, like this is obvious, like this is basically saying a function plus a function, or a variable plus a variable. Well, to be honest, these are functions, actually, to be accurate. These are functions, yeah, because you're deriving with respect to a single variable, so there's no way that the derivative would affect both. You're deriving with respect to a single variable. So when you do dy over dx and you have some variable z will be counted as a constant because you're deriving with respect to x. This is something that you might have not heard of, but this is why you have something like partial derivatives, in which, I mean, let's not touch on that. I mean, z actually might not be counted as a constant. It might be just z prime, but anyways, let's just skip that. So here you have the sum of two functions, so you derive blah blah. I don't need to touch on this probably. And here your famous rules, very important, very important, to be honest. You can use these rules to derive other rules. By derive, I'm not talking about derive, I'm talking about derive, as in you go from one step to the other. And yeah, pretty much this is the rule that we have talked about from before. This one's really special, to be honest, especially that you're talking about trigonometric functions. These are really special. These are used in multiple regions of sciences. You have multiple uses for them. So derivatives are really important here, and like it's a very crucial aspect. You use it in multiple careers and so on and so forth. So anyways, and they have many uses. Here they are saying that they'll be using these tools right here, to prove sine x, that it's cosine x. Here they're using a because they used here a, but anyways, so here they're using the formal derivative that we talked about in the beginning, and sine of an angle plus an angle is seco cosi, and they flip the h and the a. I mean, they flip the sine and the cosine, like, because I said seco cosi, here they did seco again. But anyways, so you know what to do, like, you know, just like do what they did. So sine a times cosine h, you can do plus cosine a times sine h, or sine h times cosine h, sine h times cosine a, same thing. Sine h times cosine, so same thing. Anyways, so minus a over h, and you continue h. Here they're going to factor these two and factor these two, because that's where you get your identities from here, and you just substitute. You get here 0, you get here 1. 0 because you're using the cosine h minus, or cosine x minus 1 over x. Here you're getting 0 because you're doing the sine h over h. So here you get, in the end, this cancels because it's 0. The entire expression is removed. This is 1, so you're left with this cosine a. Pretty much. This is, they're deriving the sine b of x. So just put b out, and you're pretty much done. Cosine of bx. Here you actually don't have x, you have an expression, so you have to derive it and put it outside, and then cosine of inside. So derive it and outside, and cosine of inside. And this one you have to do product rule, and then do once you're done, or for every single time that you say derivative of this, you take this out, you derive it, you do cosine of this. And now we're talking about derivative of y equals cosine bx. Now for that one, there's one thing you need to know. If you don't, then I'll refresh your mind, and if you don't remember it at all, then I'll be teaching you something new. So sine and cosine are very, 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 very similar to each other. It's like brothers and sisters, or twins, you can say. Let me just fix my graph. Okay. So this is your sine, this is your cosine. I'm very careful about where I place my points, because they're supposed to have a phase shift that's continuous, that is, I mean, constant. This phase shift is constant. Looks like a 3D slide, to be honest, and it looks nice. So anyways, so this is how things work here. So you have the sine over here. How do I know? Sine starts from 0 and just keep going. Cosine starts from 1 and just keep going. So your phase shift is this value over here. How do we know this value? Well, this is sine, this is cosine, right? So what value of sine gives me 1 here? Well, the first one comes to mind is 90, and that 90 in radius is pi over 2, so that'll be pi over 2. So the phase shift is pi over 2. But how are we gonna write it? Well, depends on what you're relating. I mean, it could be x minus pi over 2. It could be pi over 2 minus x. Depends on who you are relating to the other. So if you're saying sine x equals, sine x is in front of cosine, so you'll do x minus. So cosine x minus pi over 2. However, you can test this on your own, by the way. Put an angle here, and you should get this true. Like the value here should be equal to that. Now we're looking for, not for that, we're looking for cosine x, to prove the sine x. Because we're trying to get, by the way, the whole aim to change cosine to sine is so that when we derive sine, we get cosine, and then from there we replace it to sine. This is the entire point, because we don't have an immediate derivative from cosine to sine, so they use this method. I believe there is an immediate derivative. It's not. I don't mean the one we use. The one we use is like predetermined. It's predefined. They already did the proof for it, and we're just using it. Like you know how you memorized sine. Derivative of sine is cosine. Derivative of cosine is minus sine. Derivative of minus sine is minus cosine. How do you do that? Well, just take the sine out. The minus out. Derivative of sine is cosine. Put the minus back in, and yeah, so on and so forth. You'll continue to get the cycle. To be honest, this is a cycle: sine to cosine to minus sine to minus cosine to back to sine. Because cosine gives minus sine, and there's already a minus, so the minus cos. These are just trivial stuff, but I'm just to refresh your memory. and to tell you stuff that could help you, like, you know, you could bring it up in your mind, you could reprove it or do this kind of stuff. Anyways, so so cosine x, here you'll have sine of pi over 2 or minus x, which is what they used to use pretty much, as you can see. They just use the fact that there's a phase shift, so that they can substitute, so that they can get sine here by getting cosine here, because when, as I said earlier, if you derive sine you get, no, if you derive cosine you get sine, but we don't know that, we're trying to prove it. So if you derive cosine, you'll just stumble upon a problem. How do you solve it? Well, what they did is that they just replaced it with sine, derived with sine, you get cosine, and then they just replace cosine back out with sine, pretty much. Sorry for the squiggles, they're talking about derivative of cosine of b of x. Again, just take b minus b out, because, no, take b out, it's x, so you just take b out, and then cosine is minus sine, so minus b sine bx, pretty much. Here we continue from the previous one. Again, it's bx, but this time it's not just x, so you have to do the prime of the entire thing. And so yeah, you prime it and take it out, cosine, you're left with a minus, and you do sine off, pretty much. This, to be honest, immediately reminded me of the thing we had at the beginning, the identity we used. Let me show you. Let me start a new one and then drag this over here. Do you see the identity? This cosine x minus 1, so let's remember it, cosine x minus 1 over x. It's the same one here, cosine x minus 1 over x. But what we had was the limit itself. Now we're gonna do the derivative. So yeah, pretty much that you just use the quotient rule, because you have an expression over an expression, or a function. So with that quotient rule, so u over v, or the derivative of that, is u prime times v minus v times u prime. Whoops, should have said the other way. So u v prime over v prime. So u prime v minus u v prime over v squared. It's pretty hard to say quickly. Anyways, so you just do that, and yeah, pretty much you just simplify and you get what you get. And here we're talking about other functions, and I hope you see the video where I simply derive them for you. To be honest, I haven't seen this yet. This is the first time I see it. So I did the derivations, and they do the same thing. We all follow the idea that you're doing quotient rule for the special ones, like for example tan and cotan. Use quotient rule to prove them to be this one's what? This one's tan, right? Yeah, so tan, derivative of tan is secant squared x, because when you do this x squared and you're left with cosine x, and you do quotient rule and you're left with cosine squared x, and those two cancel each other out, because simply not cancel, but like minus minus makes plus. Cosine squared plus sine squared is your famous identity, which gives you 1, so yeah, that's how you left it. Anyways, I explained it in the video, and yeah, pretty much. And here you continue, blah blah, same thing. You also get 1, but you factor out the minus, you put it back in, you get minus 1. Here you have sine squared x, again sine is cosecant and cosine is secant, and then you just keep the square. Here same thing, again quotient rule, blah blah, you get with this. Actually, to be honest with you, you don't need to do quotient rule, you can just do chain rule. Cosine x minus 1, and then you just follow what I did in my other video. And yeah, you continue cosecant sine x, again chain rule, no need for quotient rule, waste of time. And yeah, pretty much you have activity 3. A pretty good practice, to be honest, It gives you, like, it first of all makes you remember them, makes you remember the derivatives, and they have a wide variety of them. Some nice exercises over here. It takes time, maybe not even 7.5 minutes, it might take 15 minutes if you want to make sure what you're doing, if not 10 minutes or something. But it's good to take your time, especially in these ones that are really important. So here it says remark, all of the differentiation rules for trigonometric functions are based on the fact that the variable is in radians. If x is in degrees, one must convert it to radians and differentiate using the chain rule. The derivative of y equals sine x in degrees is given by y equals pi over 180 degrees of cosine x in degrees. A nice remark, and we'll end the sections. I mean, we just have basically summaries left. A nice list of summaries that you can use, but to be honest, this one's not as important. And the next one has the list of derivatives that you might need to know. So this is a pretty good summary right here. You can screenshot it. And this is just a simple explanation, and we're done here. So thank you all, and yeah.
Hey guys, so today we're doing 3.1.1, where it's about extreme values, as in minimum and maximum, and absolute maximum and absolute minimum. So there will always be a maximum or a minimum over a closed interval. It's necessary that it be closed because otherwise there's no such possibility that it could occur. For example, if you have this, sorry, I should have drawn that better. And then you have the interval, let's say 4 and 1. Now, if you have an open interval where these are empty endpoints, and you have this function, so as you can see, the max values are supposed to be for this interval at the endpoints, but since they don't exist, this function is not even said to have a max value for this interval. So that's why it's important that it be closed. But even if it's open, sometimes it could have minimum. For example, in this case, you have this function here. So at this x value, it has a minimum. And then also, you have to make sure that it is a continuous function. Sorry for my handwriting, but it's a tablet, so what can I do? So let's say you have this, and then you have the interval. What if it extends to infinity? So like here, and then it approaches here. And this is the tangent, like 1 over x minus 4, where this tangent is 4. It's not the exact graph, but that's the idea. So if it extends to infinity, it doesn't have an absolute minimum, because that will be infinity, and infinity is not a number. It's not a real number. So in this case, it would have a maximum over here or over here, depending on which one is greater. Okay, so how do you find these extreme values? There are two cases. One, where the extreme is a critical point. You have to consider both. And the other, where it's the endpoint. So the endpoint, it's pretty simple. If you have a closed interval of -2 and 2, you just sub in f of -2 and f of 2, and you see which one is greater, and then you keep it. And then you check the critical point as well. So critical point is anywhere where it has the derivative equal to 0. So f prime of x equals 0. So you just check that, and then you compare it with the endpoint. And then also, it's where it's not defined. So it's where it's undefined. And the case would be if we had an x-axis and then the interval here, and then what if it was like this, and then so in this case, this is undefined, and that's supposed to be the maximum, but there is no maximum in this certain circumstance. So let's do an example. So here we have a function and the graph is given to you, which makes things a lot easier, and you have to find the absolute maximum, absolute minimum, local maximum, local minimum. So let's start from left to right. Here you have an endpoint, and then you compare it with all other points. It seems to be the lowest. So this one here is the minimum. The absolute minimum. And then you just keep going and look for significant points. So you go up, 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 nothing. And then you have this point here. It seems to be the maximum, absolute maximum and local maximum, but it's undefined. So it's neither. It can't be anything. And since this would have been the top value, this whole function doesn't have an absolute maximum. So there's no maximum. And then you just keep going down. Here you have this point. It doesn't seem to be the lowest minimum because this absolute minimum was the lowest minimum, but it is local. And then this one, it's the local max. And then here it's the local min. And then this endpoint, it has no significance because there are points greater than it and there are points lower than it. So that's one example. And then another example where the graph is not given. So to find the extremes, like we said, you check critical points and endpoints. So for endpoints, f of -5 is equal to, you take your calculator out because 5 is a bit too high. 1885, and f of 3 is 237. Now that's the endpoints. You have to check critical points where f prime of x is equal to 0. And the f prime is 12 x cubed minus 2. And the x values for that are cubic root of 0 of 1/6, and that's the only one. So you just sub this x value into f prime of x, and that is minus 0.8. So you have these three numbers. 1885 is the largest, so this is max, and this is the lowest because it has a negative, so min. And that's how you solve it. I'm sorry for the messy, but my tablet is glitched. Okay, so for 3.1.2, it's about the mean value theorem. So the mean value theorem states that there exists x value of c in the interval a comma b such that f prime of c equals f of b minus f of a over b minus a. So this is dependent on it being continuous and differentiable. That's the mathematical meaning. If you don't understand, let's look at it visually. Over here, you have this endpoint and you have this endpoint. If you draw a secant you draw a secant, it has a slope. Now, somewhere in this interval, since it's continuous and differentiable, somewhere in this interval there is a point with this exact slope, and it's supposed to be somewhere over here. Visually you can tell. Yeah, around that way. It's a tangent, by the way. Tangent. It's this point somewhere. So yeah, this is basically it. So this point to this point, you find the slope by using this formula, and there exists a point where it has that exact slope that is instantaneous. So the derivative at this point is not zero, is equal to this slope, and that is the mean value 0. Now the next thing is Rolle's theorem, where if f of a equals f of b, there exists c in between a and b, where f prime of c equals 0. So c is a local maximum or a local minimum or a saddle point at that point. So it has to be continuous and differentiable. So if you go over here, you can see why. You have these 2 points, and somewhere you have a point where the derivative is 0. Since they're equal, something must happen. So let's take many different formulas, or many different cases. So what if it goes up here like this, like this? There are 2 points. What if it's a straight line? Then the whole thing is 0. The whole thing has a derivative of 0. So the next one, half x squared plus 1. Okay, so how do you know that there is a value between 1 and 2 such that, like, prove that there is find the value between 1 and 2 such that it has the slope between 1 and 2. So you do f of 2 minus f of 1 over 2 minus 1. So that is half of 4 plus 1, so 3 minus 1.5 over 1, so this is equal to 1.5. And then you find the value, so you do derivative, so half times 2x equals 1.5, and x equals 1.5. So the point where the slope or the tangent has a slope of this secant over here is where x equals 1.5. So you just substitute it in the function to get the y value, and you get the point. That's it.
To section 3.3.3. Let's do the first example just to learn how to do the questions in this section. Basically, what we want to learn in this section is how to draw the graph of a trigonometric function. So example 1 says, study the variation and draw the graph of y equals 1 plus cosine x over 1 minus sine x. One important thing in this question is they haven't mentioned from which, like what's the domain in which you have to draw the function. Usually they would say from x0 to x2 pi, x pi to x2 pi, blah blah blah. But if we just blindly follow this question, we'll draw a graph from x minus infinity to x plus infinity. Now we don't have the time, nor can we draw such a graph. So let's just focus on trying to create a domain. Let's define a domain first. So we should all know that sine x and cosine x both are periodic of 2 pi, or periodic with period 2 pi. Basically what that means is they repeat every 2 pi. For example, sine is like this, it repeats. So 0, 2 pi, and then it just keeps repeating like this, blah blah blah. So that's what it means, they're periodic of 2 pi. Well, if sine x is periodic of 2 pi, 1 minus sine x would be periodic of 2 pi, right? And the same goes for 1 plus cosine x. So first step is always to show this. Since f of x plus 2 pi is equal to this, which is equal to the original function, we can say that this function is periodic with period 2 pi. That's why if we can just draw from 0 to 2 pi, it's enough to, we know how the function will look until infinity. Now another thing to look at is we have what do we say, a denominator, and if anything makes this denominator 0, our function is not defined. We have a vertical asymptote. So we just say this, so sine x equals 1. If we shift sign, we should get sine x equals pi over 2. So that means that, or sorry, sine x equals sine pi over 2. That means that x is equal to pi over 2 plus 2k pi, or minus pi over 2 plus 2k pi. Well, we should always look at this scenario. So now we can immediately see that pi over 2 does not work. It is a vertical asymptote. So if you can see on the graph, pi over 2, we have a line drawn here. It's not defined. Now, many of you will probably have questions when it comes to this part. So why are we taking the derivative? Well, we should know when the graph is going upwards, when is it going downwards, blah blah blah, in critical points, is it a local maximum, a local minimum, etc. Right? So we know how the graph is drawn. So we should all know how to take the derivative. Y is equal to u over v. U and v are both functions, so it's u prime v minus v prime u over v squared. I'm going to assume you guys know this. I'm not going to solve. But now this is the derivative. Now what do? We equate it to 0. A function that is a fraction is only equal to 0 when the numerator is equal to 0. So now I'm just going to solve this part because in the textbook it's a bit hard to understand. So let me just solve it for you guys. Now I've included this here as well. So we have this equals 0. So if I take sine x to the other side, I have sine x equals cosine x plus 1. Square both sides, I should get sine squared x equals cosine squared x plus 2 cosine x plus 1. Now sine squared x is 1 minus cosine x, cosine squared x, sorry, plus 2 cosine x plus 1. This cancels. You take minus cosine x to the other side, you get 2 cosine x squared, sorry, plus 2 cosine x equals 0. 2 cancels. So now we should solve this and we should get two possible answers. Cosine x equals and cosine x equals minus 1 and 0. So that means cosine x either equals cosine 90 or cosine x, or let me just keep it in radians so it's easy, pi over 2, or cosine x equals cosine pi. Now we should remember, if cosine x, let me just try the formula here, equals cosine alpha, for example, x is equal to plus or minus alpha plus 2k pi, right? So using that exact same thing here, we should get pi over 2 plus 2k pi minus pi over 2 plus 2k pi, and our bottom two equations would be pi plus 2k pi and minus pi plus 2k pi, right? Now if we solve this, we can immediately see for k equals 0, pi is accepted because it's between our limits 0 and 2 pi. Pi over 2 when it's 0 is accepted. You can see here you get the same value, pi minus pi plus 2 pi. Minus pi over 2, 0 doesn't work. 1, 3 pi over 2 again doesn't make sense, so we should only keep these two, right? And now if we just make a quick, or you know what, I'm just going to use the example in the book. If we would just use this thing, the variation table of variation, we should always make sure we get the the y values of our endpoints. So we should get that, f of 0 is 2 and f of 2 pi is 2, and then we can just do the table of variation and draw. This part is easy and that's all that's required. So now let's test your knowledge and let's do question book number 5 part B, and I'll let you guys solve it for a few seconds and then we'll check together. Okay, let's do it together. So now we have f of x equals sine 2x plus cosine x. Again, we have to do the domain. So now we should say f of x plus 2 pi, which is sine 2x, x plus 2 pi plus cosine x plus 2 pi is all of this equal to f of x. Since we have that, our domain is only 0 to pi. Now since we have that, we should obviously get f of 0, which is equal to 1, and f of 2 pi, which is also equal to 1, right? Now we have to derive, right? So f prime of x is equal to 2 cosine 2x, minus sine x. Now we should set this equal to 0. Now cosine 2x is equal to 1 minus 2 sine squared x minus sine x equals 0. If we just simplify, we should get minus 4 sine squared x minus sine x plus 2 is equal to 0. Let's just continue on the next page. Now that we have this equation, if we just solve this equation, we should either get sine x, the first answer, is equal to minus 1 minus radical 33 over 8, or the second answer, so solution could be sine x equals minus 1 plus radical 33 over 8, and now what we should do is shift sign up and down. So shift sign is equal to, let's do that right now. One second. We get minus 1.003 in radians, obviously. And for the second one, shift sign minus 1 plus radical 33 over 8, we should get 0.635. Let's keep it 3 decimal places would be nice. Now we should know that if sine x equals sine a, then x is equal to a plus 2k pi, or x is equal to pi minus a plus 2k pi, right? Going up here, let's just use x1 equals both parts of this equation, and then x2 equals, and then let's have this third one, x2 equals, right? Fourth one, sorry. So we have minus 1.003 plus 2k pi. We have 0.635 plus 2k pi. Now let's just do pi minus. So pi minus 0.635 is 2.507 plus 2k pi. And now pi minus 1.003, pi plus, because it's negative, 4.144 plus 2k pi. Now immediately we reject when k is 0. When k is 1, it makes sense. So let's just try that. Minus 1.003 plus 2 pi, we get 5.280. So this is our first accepted, second accepted, third accepted, fourth accepted. So we now have a total of 4 possible answers. Now immediately what you guys should do is you should find the y values of these by substituting in the equation. I have done that in advance, and now let's draw the table of variation. X, y prime, and y. So in the beginning we have 0, 1. and then we have 0.635, 2.507. It's better to put, you have to put this in ascending order so it makes sense. 4.145, 5.28 because 280, and 2 pi. Right, now this was also a 1. Let's just draw it down a little. 1, right? Now this was 0, 0, 0, 0, and now let's just find the y values. This is 1.76 minus 1.76, 0.369 minus 0.369. It's just simple substitution. Now a better thing to do would be to find the sign of the derivative of y prime at the endpoint, so you know if it's sloping upwards or downwards at the end as well. So here it's positive. Let me just do that so it makes sense, and here it's negative. So after 2 pi it's going to go down, and or during 2 pi it's going down, and after this is plus, sorry. So during 2 pi is going up, and during 0 is also going up. Now this is plus, this is minus, this is plus, this is minus, and this is also a plus. So it's going up, down, up, down, up, right? Now that we have all of this information, we should graph it. So let me just create a straight line now. Let's call this the y-axis, the x-axis 0. Now let's just create 1, 2, 3, 4, 5, and let me just make this line a little bit longer. 6 and 7. 0 would be here, 2 pi would be approximately here. I'm not going to do this to scale, it's just a rough sketch. 1 and 1, these are our easiest points. So we had 0.635 approximately here, 635, that corresponded to 1.76. So that would be here. Then we had 2.507, which corresponded to minus 1.76. So here, if you want, you guys can find the x-intercepts, but it's not that necessary because you already have a very good graph with this. 4.145, 0.369 here approximately, and then 5.28 and minus 0.369 minus here. All I have to do is connect the dots, so you get a rough graph looking like this, and this increases, and this like this, and this is how the graph looks like. Let's start with section 3.3.4. So first, we know that this section is about parametric functions. For example, x equals 5t and y equals t cubed, right? Because sometimes when we have to describe certain functions, it's not always possible to describe every point in x in terms of y, or sorry, every y point in terms of x, right? Sometimes we need that intermediate value, also known as a parameter, in which case we're using t, to give us a better representation of this relationship. So first, let's just learn how to take the derivatives, and then we'll do one grid question as an example, and to see if you guys understood or not. So first of all, what you have to do to get the derivative, or dy over dx, as it is commonly known, or y prime, the first derivative, what you have to do is find dx by dt and dy by dt. So while we just have to use normal simple differentiation. Assume that t is your variable, so it's 5, and this is 3t squared. Pretty simple. Now here's where the step comes for how to find the first derivative. Dy by dx is equal to dy by dt divided by dx by dt. How does that work? Well, it makes sense because it's dy by dt times dt over dx, because you're dividing, so the reciprocal, it obviously cancels, so you get dy by dx. So you use the exact same rule, you get 3t squared over 5, and that is your first derivative. This equals y prime. Well, sometimes they ask us for d squared y over dx squared, or as this is also known as y double prime. Now the formulas that I'm using here are a bit different from the book, but this makes it very easy to work out. Well, the formula for this is dy prime by dt, all of this over dx over dt. So dx by dt remains a constant denominator, and this you have to derive y prime. This is the derivative of y prime. Well, for that you have to derive that 3 over 5 times 2 is 6 over 5t. All of that over 5, if we can simplify, 6 over 5t times 1 over 5, leading us to 6 over 25t. Excuse me. And this is the second derivative. Now let's make sure you guys understood it by doing.
Okay, so question 18. We're given a function that has two pieces and it splits at -1. It's also differentiable at that -1. And we're asked for the value of -2, f of -2. F of -2 is in the smaller piece, and thus why you're doing all this trouble. Otherwise, if it was greater than like 2, you would just immediately put it here and find the value. So the word differentiable tells you two stuff. Is that the function's left-hand derivative is equal to its right-hand derivative at that -1. And also, it's necessarily continuous. And then the rule for the continuous is that the limit, the left-hand limit at that point, or at that x, is equal to the right-hand limit, or the right limit at that point again. So with that, we'll just equate the two polynomials for the continuous. So ax cubed plus bx plus 11 equals -2x plus 1. We're told that x is -1, so immediately substitute. So -a minus b plus 11 equals -1 times -2, that's 2, 2 plus 1, that's 3. Now let's take this to the other side, to the other side. If you want, you can also multiply by minus and operate, it's fine. Other way you get this, a plus b equals 8. This is your first equation. The second one you get from the differentiable, as we said, so differentiate, you get 3ax squared plus b equals -2. And then just substitute -1, you get 3a plus b equals -2. This is your second equation. What you can notice is that you can subtract the two equations to remove the b's. So in this case, if we subtract, we get 2a equals -10, because -2 -8, yeah. So a is -5, and b substitute into that, the other one, because it's easier. So -5 here, you take it to the other side, that will be 13. So the equations themselves are, well, I'm not going to write this one because I will not use it. It will be -5 into, well, we're looking for -2 cubed plus 13 into -2 plus 11. Now this is, well, if we calculate the value, just give me a few seconds, -5 into -2 cubed plus 13 into -2 plus 11, you'll get 25. And this is your answer. Question 19. So we're given a function, again, two pieces, and we're asked for these choices, differentiable, continuous, blah, blah, blah. And so let's do them step by step, and let's see how we can eliminate them. F of x is not differentiable at x equals to 0, okay, because f of 0 does not exist. This sentence makes sense, but let's check if it's right. F of 0 does not exist. Now that's a bold statement. Let's check if it's right. So for this to exist or not, you have to check, first of all, is 0 a possible value? Yes, it is. Now, does f of 0 exist? Well, let's put 0 times 4, 0, plus 1, that's 1. So 1 is a value, so it definitely exists. So this statement is wrong because this part is wrong. F of x is not continuous but differentiable at x equals to 0. This statement does not make sense. It's not logical, so you don't need to read it again. It's just any differentiable function is necessarily continuous, so if it's not continuous, it's necessarily undifferentiable. Now for the second one, or the third one as in, f of x is not differentiable at x equals 0 because it's not continuous at that point. Well, we put here 0, we got 1. Let's put 0 here, we get 0. Now the limits are not equal. 1 here and 0 here. So I'm not sure in the order. Well, we said 1 here and 0. So it will look something like this. Whatever, be it a line or anything. Well, actually it's a line. It will look something like this. And then honestly, I'm not sure. I think something like this. So this is jump discontinuity. So with that, this is not continuous, you're right, and that is the reason why it's not differentiable, because it's not continuous. Of course, there could be another reason, which is like maybe it's not differentiable, but we don't need to check that for now. Yes, it is because it's not continuous. Now for 4, it's differentiable. Well, we just said no. So the limit of this does not exist. Well, it sure shouldn't, because then again, pay attention here. It's saying h, not h. It's working with h and 0, not 0 plus or 0 minus, because it's just saying that it's differentiable or not. But if it has 0 plus or 0 minus, right hand differentiable or left hand differentiable. Why is that? What does that matter? Because the function could be differentiable at a left hand or a right hand, but not differentiable as a whole. So check if it says these kind of statements. I'm not sure what to expect, but again, if the exam ends up being something tricky or something horrible like last time, so just make sure that this is 0, which means it's the function. If you're talking about the function, you're just doing the same as here. You're addressing the function itself. So again, not continuous, so does not exist. 1, this is right. So we said 3 and 5 until now. 6 exists, definitely not. So there you have it, we're done. 3 and 5. Okay, so question 20. Again, function, 2 pieces, and same style of questions. F of 0 exists, let's check. 0 is defined. Put 0, you get 1. 1 is a defined value, so there you have it. It does exist. It's true. Next one, limit of f of x as x approaches 0 does not exist. Let's check. So put 0, 0, you get 1, 1, and they're equal, so the limit does exist. They asked for not, so it's false. So we don't do anything here. So we don't pick it, basically, it's false. So for the third one, they're asking for the derivative of the function f of x, and that does not exist. So let's double check that. Derivative of this piece is 2 equals derivative of this is minus 2x. So equate them and replace 0 instead of x. So you get here 0. Is 2 equal to 0? Definitely not. You have 2 different slopes. I don't know how to draw it. Well, not yet. I mean, I can take time, but there's no point. They're not equal. So again, this is true. The limit does not. The derivative does not exist. 4, is it continuous? Yes, we said it's continuous from here. I can show you again. Put 0, 0, you get 1, 1, so they are continuous. It's a single flow, no matter how the function goes, which is probably something like this. Like this is the point where they merge or something, but it's continuous either way. So anyways, for 5, is it differentiable? We just said no, it's not. So 5, no, they said is differentiable, so this is wrong. So there you have it, 1, 3, 4. For 21, to be honest, my concern is not the minus 3x times cotan x, like product rule when you do the derivative. My concern is the cotangent x itself, because the product rule is really easy. But let's just do it. So product rule. So it's y prime is u prime times v plus v prime times u, keeping in mind that I picked u to be minus 3x and v to be cotangent x. Multiplication is commutative, so choosing u and v doesn't make a difference here. The only difference is that just the position, especially when you're doing quotient rule. So anyways, derivative of minus 3x, that's minus 3, times v itself, nothing to change, cotan x, plus v prime. Now this is the main concern. The answer is minus cosecant squared. But don't worry, I'm not leaving it here. After this question, I'm deriving all of them. There are 3 of them, and I'm doing that really quick, to be honest. So, and I'll tell you why it's important to know that. So minus 3x, you keep it the same because you derive the other one. And then this one's minus 3 cotangent x. Minus minus makes plus, so plus 3x cosecant squared x. With that, you replace pi over 4. Pi over 4 is 45. tan of 45 is 1, so cotan of that, which is 1 over 1, which is 1, times minus 3, that's minus 3, plus cosecant is nothing but 1 over sine. Yeah, 1 over sine. So sine of 45 is radical 2 over 2. 1 over that is radical 2. So you will have 3, well, x is pi over 4, sorry, times, we said this is radical 2, so radical 2 squared. I was gonna remove it, but anyways, radical 2 squared, this and this cancel, so you're actually left with 2. 2 and 4, this gives 2, so you're finally left with the simplest form, minus 3 plus 3 pi over 2, which is approximately, if you do it in the calculator, let me double check, it is 1.71. So 1.71, they want whole number, here, right here, where is it, yeah, nearest whole number, so 2. Officially with this question, we are done. But however, I want to show you how you can do the derivatives for sine, cosine, and tan. You know the answers. Well, at least for tan, not exactly. But don't worry, I'll be showing you sine and cosine. You know, like sine is going to be my cosine, and cosine is going to be minus sine. But let me show you how we can derive tan, cosecant. Let me just write them all fully. Tan, cosecant, and secant, and finally cotangent. Because the thing is, if you at least see the way a few times and derive it yourself, even if you don't recall the answer itself, like when you go to the exam and they go like derivative of secant, and you mix it up with cosine, with cotan, you forget what trigonometric function to use, like in the derivative, what do you put as the answer. So if you remember the derivative itself, or at least like the process, even if you forget, you can do it again. For example, myself, I can't remember things easily, so I usually tend to derive most of them. And I don't remember the answer, but I mostly remember the way, so I just rederive it quickly. And by the way, it can be pretty fast. It will be sometimes similar to just recalling it, but like I do the way in my mind, and I'm like, okay, so you move this, you derive this, you move that, oh yeah, you get this. Like the way sometimes gives out the answer. So yeah, so let's do tan of x. How do you derive that? Well, tan for sure is sine x over cosine x, no doubt about that, right? So let's try doing quotient rule in this case. Quotient rule, again, v and u. I'm just going to skip into the process itself. So derivative of this is cosine, and there's a cosine here because you do actually it's fine, let me just do them one by one, not to miss anything and for you to perfectly know what I'm doing. So it's u prime times v minus v prime times u over v squared. Now let's write that out. So u prime, u is sine x, derivative of that is cosine x, okay, times another cosine x, I don't need to put parentheses actually, plus c's and parentheses make confusion, so I'm just going to leave it like this. So cosine x minus derivative of cosine, which is v, you get minus sine. Wait, I just said minus sine, right? So we'll make this positive because there's a minus here and there's a minus from derivative, and you get yeah, sine x times sine x itself. So let me just write it like this. Same thing here, cosine x, cosine squared. Again, no need for the parentheses. If you're confused, you can pause the video and just try doing it yourself. You see what I did. Okay, let's just rewrite this part. So we said cosine, where's the thing? Yeah, so we said here cosine squared x plus sine squared x. So let's rewrite that part. So cosine squared x plus sine squared x over v squared, that's cosine, so cosine squared x. Now, how can you continue from this step? Well, for sure, doesn't this ring a bell? Well, it should. So it will give you 1 over cosine squared x, and that cosine, 1 over cosine is secant, so this is secant squared x. That's done. Check your tables if you have any of them, or on your calculator or anything. It should be secant squared x. That's done. Let's do cosecant. So cosecant of x, yeah, I hate this C's and parentheses, man. Anyways, so the derivative of that is, well, secant for sure is 1 over sine, right? Derivative of that, well, some of you might say, oh, like the previous one, quotient rule. Perfectly correct, but I prefer it's much faster if you just do chain rule in this case, because 1 is a function, sure, just like how this is a function here, but you know, like a derivative of 1, it's not really important, so you can immediately skip to chain rule. So minus 1, that's right, and yeah, pretty much derivative of this. So just drop the minus 1, so minus 1 here, and then put 1, just subtract from the coefficient, so you get sine squared x, okay, times the derivative of sine itself, so that's cosine x. Here, cosine over sine is cotan, so we can write minus cotan x, and then you're left with another sine, 1 over sine basically, so that would be cosecant, so cosecant x. Let me just double check quickly. Okay, so we're doing cosecant, and yeah, pretty much it's minus cosecant cotan x. Same thing here, just to double check so that I wouldn't do something wrong. And what are we left with? We're left with secant. We'll just do this quickly. Secant of x, derivative of that would be same thing, it's 1 over cosine x, derivative of that. Again, just do cosine minus 1, derivative of that. I'm not going to write the x because it's kind of annoying. Anyways, so minus 1, cosine, you just have to hear cosine squared, because you know, like minus 1 becomes minus 2, so it's over the denominator and it's 2 here, and derivative of cosine, that's minus sine, minus cancels, so sine over cosine, that's tan, and you're left with a cosine down, which is secant, and that should be your answer of secant. Again, let me double check. Secant is tan x, secant x, correct. Now for the final one, cotan. For cotan, you simply just, let me just write it, cotan x is cosine over sine. This is another one that needs quotient rule, just like the tan. They're brothers or sisters, however you want it to be. So yeah, so you have to do the quotient rule here. So let's do this mentally. Derivative of this, sine. Sine times sine, sine squared. Sine squared, okay. Let's continue. Derivative of this, cosine. Cosine times cosine, that's cosine. There's a minus here, but wait, I just did a mistake. We said derivative of cosine is not sine, it's minus sine, sorry. And sine here, yeah, so minus sine, because derivative of cosine is minus sine, so minus sine times sine, that's minus sine squared, minus sine, derivative of sine is cosine, times cosine, so that's minus cosine squared. Yeah, now it definitely makes sense. That's why I paused. I was like, what? You're not supposed to get that. So anyways, let's factor minus 1 out. You're left with sine squared x, sine squared x, no, actually let me write it, plus cosine squared x. Sheesh. So with that, you can notice there's something here that you can do, a very special thing. We all love simplification, man. We don't hate, we hate it for it to be long and difficult. So this is sine squared plus cosine squared, that's 1, that's the simplification. So minus 1 over sine squared x. Sine, 1 over sine is cosecant, so that's minus cosecant x squared. And there you have it. We did the derivative of tan, derivative of cosecant, derivative of secant, and finally derivative of cotan. And the rest are sine, cosine. We said they're really easy. We're using them. So, whoops. Anyways, so thanks to that, we can basically get any question we forget. For example, let's say I personally haven't memorized any of the answers that I just derived. So for example, when they ask me secant, give me the derivative of secant, I go like, secant, we did 1 over what? Well, first of all, secant is 1 over cosine. I remember when I did this one and I put the cosine and derived it, you get the minus sine, and then like you can do it mentally, or you can just write it on the paper quickly, like you derived quickly, you go like anyways. So with that, I hope it helped, and we'll move on to the next questions. Okay, so for the last question I'll be doing in the grid here, in this one, not the AP. So y is 3 cotan pi minus 6x. We want to find the derivative at pi over 24. So first of all, if you've seen the video where I derived the tan, cosecant, secant, and tan, cotan, you will be able to like for me, I haven't memorized the cotan, for example, in this case, but I remember it's cosine over sine, and the derivative of that, you do this. I remember you get sine squared and minus 1 over that. So I remember the answer, well, not I remember, from this I know that the answer is going to be minus cosecant squared x. So I didn't memorize it, but I got this immediately by remembering the process I went through. So this is one nice way of, or one nice benefit or advantage of doing the derivatives, or like deriving. By deriving, I don't like this is a coincidence that the word derive has double meaning here, but I mean to get the equation through, you know, doing processes and calculations. So anyways, derivative of cotan is minus secant squared x. But here we have something other than x, so we'll have to do it step by step. So first of all, 3, okay. 3 times, 3 just, you know, give it, like put it away, it's just 3. 3 times, well, cotan of pi minus 6x. Let's do this first of all. The derivative of cotan pi minus 6x. Derivative of that is minus cosecant squared of pi minus 6x. But you also have to do the derivative of this, the x itself. Like x, I mean, this is x and times x prime. So derivative of this, pi, you get 0, so here you get minus 6, so minus 6. Minus and minus cancel. 6 and 6 give you, 6 and 3 give you 18. So 18 cosecant squared pi minus 6x. So pi over 24, so let's do this. Put 24 here. So pi over 24. This and this cancels, you'll have to deal with 4. So pi minus pi over 4, so 3 pi over 4. Yeah, 3 pi over 4. No. Wait, what? Let me just do this quickly. Minus pi over. Yeah, 3 pi over 4, right? So with that, cosecant is nothing but 1 over sine. So let's do the sine of pi over 3 pi over 4, which should be the same as pi over 4, which is either way. So you get radical 2 over 2. So that's radical 2 if you flip it. So radical 2, and then you square it. So that's squared. If you want to see the steps would be 1 over sine squared x. That's 1 over radical 2 over 2 squared. If you flip, you get radical 2 squared, which is what I had here. So times 18. Times 18, you will get, this is 2, so 2 times 18, you get 36. And that should be the answer.
Okay, so for number 23, we have to find the difference between the maximum, absolute maximum, and the absolute minimum. So to find the maximum or minimum, the extremities or the extremes, we look at the critical points and the endpoints. Now, if you look here, I substituted the endpoints already and found the respective f of x values. But now we have to check the critical points. So since this is a polynomial, all you have to do is check the local minimum and maximum and the saddle point if it exists. So equate the derivative to 0. So either x equals 0 or x equals minus 2. So now you just substitute it in. So f of 0 is equal to 0 and f of minus 2 is already given, so 12. So in the closed interval minus 2 to 1, you have 12 and you have 0 and you have 0, sorry, not here, you have 0 and you have 12. So 0 is the minimum, 12 is the maximum, so 12 minus 0 is equal to 12, and that is the answer. Okay, so for number 24, they give you the sine function and they ask what is the smallest possible positive value of k for the function has at least one point c in where f prime is 0. So since this is about mean value theorem and Rolle's theorem, where if you want to find the point or the smallest interval between 0 and this, 0 has a sine value of 0, and then you have to find another sine value of 0, so that way you can have the secant equal to 0 because it's a straight line, and then one of these points by mean value theorem will have f prime of c equal to 0. So you just have to find which function makes it 0 again. So 4 sine x over 4 equals to 0. So 4 is cancelled out because this whatever makes sine x over 4 equals 0. So sine is 0 at 0 and pi and 2 pi, so forth. But they asked the smallest interval, so 0 is there, so pi is what we have to find. So x over 4 equals pi. So x equals 4 pi. So k is 4 pi. Next question, 25. Consider the function over the interval 0, k. What is the value k for which at least one point in the given interval where f of prime of c equals 0? So the same thing, you have 0 and you have k and you have to find which one, which is the interval that has a slope of 0, which has a tangent that is slope of 0. So the same thing again, you equate it to 0. So minus 2x squared plus 14x equals 0. Now x is out here, we can just take this out, so minus 2x plus 14 equals 0, so x equals 7. Okay, so for number 26, they give us a tan function and ask about its continuity and differentiability. So they ask for 0 to pi, 0 to pi, 0 to pi, 0 to pi. So 0, it's actually pretty normal. You have this function here, and it just looks like a polynomial function. But pi is where it gets confusing. So at pi, it's actually infinity. But from the left of pi, it just keeps approaching infinity. So it's not continuous at pi. So for the first one, when they say 0 comma pi, pi is not included. So that's why it's correct. Is it differentiable over the interval? Well, to do that, you'd have to get either physically calculate the derivative. So it'll be like secant something, secant squared ax, so half times 2, so this is cancelled, secant squared x over 2. So then when you substitute pi over 2, you get 0, and then it becomes 1 over 0, so infinity. So it's not differentiable at pi. But since there's a bracket here, it's fine. Is it differentiable at x equals 0? Yes, because if you substitute 0 in here, you will get 1 over 1 squared, and that's 1, so it's allowed. And then here, this is where they include the bracket. So is it continuous over the interval with pi included? No. And there exists at least one value such that the secant between this and this is equal to that. No, that doesn't exist because it's not continuous on the closed interval and it extends to infinity, so there is no point when it extends to infinity.
By doing grade question number 27 as an example, I give you guys a few seconds and you can solve. Let's solve it together. Consider the function given parametrically by x equals square root of t, y equals t squared, t is greater than or equal to 0. Why have they given us this? Because it's in square root, so obviously it has to be greater than or equal to 0. D squared y over dx squared, or y double prime, is equal to kt, where k is a whole number to be determined. What is k? So first, before finding y double prime, you have to find y prime, which is dy by dt, all of that over dx by dt. So let's find dy by dt. That's the derivative of y, so that's 2t, and dx by dt is t to the half root t, right? Yeah, that's correct. Now we just have to do 2t over half root 2t. If we just simplify like this, we get t is half, so 4t 3 over 2. Or we can do, let's just keep it like this so that it's easier to derive. 4t to the power of 3 over 2. Right? Now let's find y double prime. That's the derivative of this over dx over dt. Well, that's 3 over 2 times 4, 6t half, all of that over 1 over 2 root t. That's 6 root t times 2 root t. Doesn't that give you 12t? And that's your final answer. So that shows that k equals 12. That's it. Question 28. Recognize the graph of a function given parametrically. We have three functions here, f of x, g of x, and h of x, where we have x and y given in terms of t. We have 6 options and we have 5 graphs, and we have to see which of the options are correct. I'll give you guys a few seconds. You guys can solve and then we'll check together. Let's solve together. Now let's move for the first one, f of x. Now we should see immediately that x is equal to 3 over 4t, which means t is equal to 4 over 3x. And that shows us that since t is there, y equals square root of 4 over 3x, right? Now what do we know about square roots? They have a limitation. X has to be greater than or equal to 0. Now from this information, we can immediately rule out this and this, right? Because these are two graphs where x is negative. Now if we see the answer, y also has to be greater than or equal to 0. We can't have a negative answer. We're not leading with I here, no. So this is also immediately removed. Now one more thing we should remember to help us finalize the answer is that the graph of y equals square root of x, that doesn't look correct. Y equals the square root of x tends to look like this. Is it an exponential function? No, it's like this. So this is wrong. This is correct. So now the graph of f is the curve labeled I. See, I'm not solving it the way you would solve in a written exam, because this is a multiple choice exam or an interactive exam. They don't need to see our working. What they need to see is basically a correct answer, right? So in short, all you need to do is reason it with it like this, and then you should get every answer correct. Let me just erase all this and let's move on to the next one. In the next question, they're saying g of x excuse me, x equals t squared and y equals t to the power of 9. Since x is t squared, anything squared is positive, x has to be greater than or equal to 0. Again, cancelling out this and this from our possible choices, right? Y is equal to t to the 9. Since y is equal to t to the 9, what is minus 1 to the power of 9? Minus 1. So y can be negative or positive. So y is belonging to the set of real numbers, in short. So it can be negative, I is wrong, it can be negative, double I is wrong, triple I is the only possible answer. And since the graph of G is the curve labeled triple I, 6 works. I'm gonna put 6 here because one more has to be the answer. So let's just see what is H now, and then we'll finalize this question. Okay, H of x now. X is equal to minus t to the power of 5, y equals t. Since y is t, then x is equal to minus y to the power of 5 immediately. Now again, you guys, if you want to find the derivative, take critical points, blah blah blah, you guys can do that. But a much easier method would be just take a few points. At 0, it's 0. At 1, you get minus 1. At minus 1, for instance, you get 1, right? And let's should we take more? Yeah, why not? For 2, you get 32, minus 32, dot dot dot, right? You should get the thing from now. Now, let's see. In curve I, we don't have a negative x. Where it is possible, wrong. Same for double I. And now let's move on to IV, V and triple I. We have seen that there is possible to get a negative 1, wrong, like a negative y. We can get a negative x, so that's wrong. 5 is the only correct answer. See, you have 0, 0. You have 1 minus 1. You have minus 1, 1. You have 2 minus 32 eventually. So, the curve of H is the curved label V. So, the answer for this question is 1, 3 and 6.